Okay, so let us continue with this question. We have a fuzzy if-then rule. If x is A, then y is B, where variables x and y take values in universes x and universe x, y respectively. Universe x has two elements, universe y has three elements, and the fuzzy set A is defined like this, and fuzzy set B is defined like this. And we are asked to consider Reichenbach implication, which is given by this. A imply B is equals to 1 minus A plus AB for all truth values A and B. And given this particular input, x equals to A dash, we are required to infer the output for the set y equals to B dash using compositional rule of inference, using generalized mode exponents um, based on compositional rule of inference. So the first step is we compute the relation R, which captures the conditionality expressed by this fuzzy if-then rule. And we do that using this implication. And how do we define R? It's essentially the outer product between fuzzy sets A and B based on the implication R, this given implication, right? And since we're computing R, we will look at fuzzy sets A and B as column vectors. So you have 0 0.7, 0 0.9, outer product of this vector with this vector 0.5, 0.3, and 0.7. And this outer product is based on the given implication. And therefore, I'm just following the definition. So outer product of this matrix 0 0.7, 0 0.9 with this matrix 0 0.3, 0.5, 0.7. Right? So we take the transpose of this matrix, and this is what we get. And then we compute the elements of the resulting 2 by 3 matrix, right? So this is how the entries of this 2 by 3 matrix looks like. And then using the definition of the given implication, I can compute the individual entries. So 0 0.7 imply 0.5 is 0.65, right? Because 1 minus 0.7 is 0.3, and 0.3 plus 0.7 times 0.5 is 0.35. So 0.3 plus 0.35 is 0.65. And similarly, if you compute the other entries, this is what you will get. And right. So now that you have the relation R, you can compute the output fuzzy set B dash given the input fuzzy set A dash. And this is how that output fuzzy set B dash is defined. It's essentially the composition of fuzzy set A dash with the this relation R that we have just computed, right? And since we are not provided a t-norm, we will assume that we are required to use the minimum t-norm. So therefore, we'll do the max-min composition. If nothing is provided regarding the t-norm, we assume that we're required to use the minimum t-norm. That is, we're required to do max-min composition. Okay. So this is our matrix R. And since we are doing the max-min composition, right? So we are pre-composing a fuzzy set with a relation. So A dash comes forward. So we will use the row vector identification for fuzzy set A dash. So A dash is 0.5, 0.2, and you have to compute. Uh, you have to basically compose this with, right? Now let us do that. So the resulting matrix would be a 1 by 3 matrix, right? It's basically would be a fuzzy set over universe Y. So let us do max of means. So minimum of 0.5 and 0.65 is 0.5. Minimum of 0.2 and 0.55 is zero point 0.2, of course. And minimum of 0.5 with 0.51 is again 0.5. And minimum of 0.2 and 0.37 is again 0.2. Minimum of 0.5 and 0.79 is again 0.5. And minimum of 0.2 and 0.73 is again 0.2. So what we end up getting is 0.5, 0.5, 0.5. Or in other words, your fuzzy set B dash, the output fuzzy set B dash has membership zero point 0.5 for all the elements of universe 5, right? So this is your output fuzzy set. Okay. Now let us see which of the given four options are correct. First option says that membership of y1, y2, and y3 in B dash are same, which is indeed true. In fact, this is equal to 0.5. Is the scalar cardinality of B dash 1? Definitely not, because scalar cardinality of B dash is zero point 0.5 plus zero point 0.5 plus zero point 0.5, and that is 1.5, which is definitely not equal to 1. So B is incorrect. B dash is normal. Of course not, because it does not assume the value membership value 1. And B dash crisp. It's definitely not crisp because you have all the membership values strictly lie between 0 and 1, right? And for a fuzzy set to be a crisp set, its membership values, the membership values that it attains should either be 0 or 1. So this is also incorrect. So B, C, and D options are incorrect, and only option A is correct. Okay. Now let's quickly make an observation. So let's stick with the example that we considered. We have universe X, universe Y. They consist of 2 and 3 elements respectively, and we have fuzzy set A and B like this, and we have fuzzy if then rule. If X is A, then Y is B. Now, it is natural to expect if your input fuzzy set A dash is A itself, then our output fuzzy set B dash should be B, right? Natural to expect. Because this is what the given fuzzy if then rule, if X is A, then Y is B. From looking at this fuzzy if then rule, it is natural to expect that that if our input fuzzy set A dash is A itself, then the output fuzzy set B dash should be B, right? Or in other words, the generalized modus ponens should extend the classical modus ponens, because classical modus ponens tells us that if you are given P imply Q and P, from there you can infer Q, right? So a generalization of classical modus ponens, or what we call as GMP, should extend this, right? In other words, if the input fuzzy set A dash is A itself, then the output fuzzy set B dash should also be B. So let us quickly see if that is the case. So we had already computed the relation R, right? And what was that? It was 0.65, 0.55, 0.51, 0.37, 0.79, and 0.73. So this was our relation R, which we had computed by taking the outer product of A and B. Now we are given X equals to A dash equals to A itself. So what would be B dash? It would be composition of A dash with R, which in other words, it's the composition of A with R. So let us quickly perform this composition and see if we actually get the, the fuzzy set B as the output. And if you do that, so maximum of min, so minimum of 0.7 and 0.65 is again 0.65, and minimum of 0.9 and 0.55 is 0.55. So if you take the maximum, you get 0.65. If you take minimum of 0.7 and 0.51, you get 0.51, and minimum of 0.9 and 0.37 is again 0.37. So their maximum is 0.51. Similarly, minimum of 0.7 and 0.79 is 0.7, 0.9 and 0.73 is 0.73. So this is what you get, right? So your B dash is 0.65y, 0.65 membership for y1, 0.51 membership for y2, and 0.73 membership for y3. And this is definitely not equals to b, right? Therefore, we arrive at a very interesting conclusion that the generalized modus ponens does not necessarily extend the classical modus ponens. And this is something that does not align with our expectation, right? So it's natural to ask under what conditions the generalized modus ponens extends the classical modus ponens, or in other words, given the input fuzzy A dash to be A itself, when when does y dash the output when does y equals to b dash, the output fuzzy set becomes b itself. And it turns out that if your fuzzy set A is normal and your t-norm I is a continuous t-norm, and the implication I that you use to build the relation R that expresses the conditionality cap expressed by this fuzzy proposition, if that implication I is the R implication induced by this t-norm I, then GMP extends the classical modus ponens. Or in other words, if we are given uh, the input fuzzy set A dash to be A itself, then the output fuzzy set B dash would be same as B, right? So this is where you see that continuous t-norms are actually special, right? And that is why I uh, made a mention of that is why continuity of t-norm and R implications are important, and that is why I mentioned at an earlier point that R implications are interesting implications, right? They satisfy the neutrality property. They also have this very um, interesting property that if you use the R implication induced by a continuous t-norm in the setting of GMP, then it extends the classical modus ponens. So let us quickly look at the proof of this. It's not very hard, so I thought that I will do this. So suppose these three conditions hold. Now, since A is normal, therefore, there exists an element in the universe X such that the membership of an element X naught such that its membership in fuzzy set A is 1, right? So this is you should remember. This is something that you should remember, right? Now, uh, how is the output fuzzy set B dash given? It's the composition of A dash with R, and here A dash happens to be A itself, so it's composition of A with R. Therefore, the membership function of B dash looks like this. So supremum, right? We are given t-norm I, therefore we will use that for our composition. And the relation R is built using the fuzzy implication I, and that is how R is defined. So this is the membership function of our output fuzzy set B dash. And we will show that the membership function of B dash is precisely equal to membership function of B, or in other words, B dash is equals to B. Now, we are taking the for computing the membership of y in B dash, we are performing this particular supremum, right? So we are taking supremum of this quantity over all x in the universe capital X. So therefore, if we take a particular element x naught of our universe X, then this supremum would be greater than equal to that this quantity at x naught, right? But this is one, and this is also one. And we know that any R implication satisfies the left neutrality property. This whole thing would become nothing but mu by, or in other words, we get this. But we know that one is neutral element of any t, no? So we'll end up getting this. Thus, we are able to show that the membership of y in B dash is greater than or equal to membership of y in B. So it suffices to show the other implication, basically other inequality, right? But this followed trivially. Why? Because we are using a continuous t now, and therefore the R implication I which is defined in this particular manner, has a very interesting property. And what is that interesting property? That supremum is attained. And therefore, I, right, and for all AV, right? This is something that I mentioned in the fuzzy section part as well, fuzzy implications part as well, right? So this property holds, right? So the denom I and the implication capital I satisfy this property for all AB in unit interval, right? And therefore, for all X in our universe, we can say, right? So here A is nothing but membership of X in A, right? And B is membership of Y in fuzzy set P, right? So this is something that can be said for all members X of our universe capital X. And therefore, the supremum, so therefore basically mu by, this quantity, is an upper bound for all these quantities, right? As X varies over the set capital X. But supremum is the least upper bound. And therefore, supremum of these quantities as X vary over the universe capital X would be less than equals to mu by. But this whole thing is nothing but mu b dash of y, right? Therefore, we are able to establish that mu b dash of y is less than equal to mu by. So we are able to show this equality and this equality. And thus, this happens. Mu b dash of y is equals to mu by, or in other words, fuzzy set b dash is equals to p. So, long story short, generalized modus ponens that we learned is not necessarily nice in the sense that it does not extend the classical modus ponens. However, if the fuzzy set A present in this rule, fuzzy if then rule, happens to be normal, and we are using a continuous denom I and the corresponding R implication of I in performing our generalized modus ponens, then it extends the classical modus ponens. That is when your input would be, when your input A dash is A, the output B dash is B. Okay. So this should give you a sense of why the an interplay between T norm and fuzzy implication capital I is important, because it helps you prove some very interesting and very desirable results. So this is the fact that the generalized modus ponens should extend the classical modus ponens. It's a desirable, thing. Okay. Now let us see if this. Let us see if the theorem that we proved actually work. It should, of course. I mean, we have already proved it, but for the sake of illustration, let us consider the example that we considered before. But in this case, the fuzzy set A is normal. The membership of X2 in A is 1. And we are going to use the minimum T norm, the standard T norm IM. And instead of using the Reichenbach implication, which we did in our previous example, we will use the R implication corresponding to the minimum T norm. And we know that, and this is something that we showed in the fuzzy implications part, that the R implication corresponding to the minimum T norm is the Gödel implication, right? So A imply B is equals to 1 if A is less than or equal to B, and it is B if A is greater than B. So let us quickly verify if given the input A dash to be A itself, if the output B dash is B. So what will be the relation in this case? So in this case, this implication R is the Gödel implication. Uh, Sorry. right? So zero point 0.4 imply zero point 0.5, it's 1. 0.4 imply zero point 0.3 is 0.3. 0.4 imply 0.5 is 1. 0.5, 0.3, 0.7, and BDAS, which is basically this. This is nothing but R. Maximum of min, minimum 0.4, 0.5, maximum is 0.5. 0.4 and 0.3 minimum is 0.3, 0.3, so this is again 0.3, the minimum of 0.4 is 0.4, 0.7, so this is 0.7. And this is precisely equals to B, right? So when you use minimum T-norm and the corresponding R implication, which is the Gödel T-norm, Gödel implication, my bad. And if your fuzzy set A happens to be normal, which in this case it actually is, then the output fuzzy set when A dash is equals to A is actually B. Okay. So I hope I gave you a sense of how generalized mode exponents work and under what condition it extends classical mode exponents. Now let us jump to generalized modus tollens, right? So it's basically the fuzzy translation of the classical mode exponents, which says that if you have P imply Q and you have not Q, then from that you can infer not P. So in the fuzzy setting, this translates to if you have a fuzzy if then rule, if X is A, then Y is B, and you have a fuzzy set B dash over universe Y, then how do you infer fuzzy set A dash over universe X? So just give me a moment, I'll connect my charger. Right? So again, this fuzzy if then rule expresses a conditionality. That conditionality is captured by a fuzzy relation R built using an implication I, fuzzy implication I. Having obtained that relation R, the question is how do we obtain this antecedent fuzzy set A dash? So this we do by post composing this consequent fuzzy set B dash. That is, given a consequent fuzzy set B dash, we infer the antecedent fuzzy set A dash by post composing R with B dash. And therefore, the formula for A dash is given by this, right? So we have already seen how to post compose a fuzzy relation with a fuzzy set, right? And again, this formula can be motivated in a similar manner as how we motivated the formula for compositional rule of inference, right? So where you look at the classical setting and then you start with a very simple case wherein the conditionality between variables x and y exists in the form of a functional relationship. And then you look at what happens when that conditionality exists in the form of a crisp relation and not necessarily a functional relationship. And from there, you generalize what happens when this conditionality exists in the form of a fuzzy relation, right? So this, I would encourage you to go back to the classical setting and convince yourself that this is an appropriate formula for ADAS. I'm not going to do that because I've already done that for GMP. Okay. Now, let us do a problem on generalized modus tollens. The setting is same as the previous question. The only difference is we are given a consequent fuzzy set B dash and we are required to infer a antecedent fuzzy set A dash. So we had already computed our relation R. The membership matrix of R was this, right? I'll refer to my notes quickly. It was 0.65, 0.55, 0.51, 0.37, 0.79, 0.73, right? So R is a fuzzy relation from universe X to universe Y, and it captures the conditionality expressed by this fuzzy if then rule. Now we know that the antecedent fuzzy set B dash is obtained by post-composing the fuzzy relation R with consequent fuzzy set B dash, right? And therefore, what we want to do is the following. Now, notice that we are post-composing a fuzzy relation with a fuzzy set, and therefore we will consider the column vector identification of the fuzzy set. And again, this is something that should occur naturally to you because we have a 2 by 3 matrix and I have to post multiply it with some vector, like either a column matrix or a row matrix. Now it's a 2 by 3 matrix. Therefore, what we should have on the right is a 3 by 1 matrix. Or in other words, we should consider the column vector identification of fuzzy set P dash, right? And since nothing is given regarding the T norm, we will consider the minimum T norm, or in other words, we'll perform the maximum composition. So let us perform the maximum composition. So we'll end up getting a 2 by 1 matrix. So max of min, so minimum of 0.65 and 0.2 is 0.2. Minimum of 0.51 and 0.3 is 0.3. If 0.79 is 0.7 is 0.7. Similarly, minimum of 0.5 and 0.2 is 0.2. Minimum of 0.37 and 0.3 is again 0.3. Minimum of 0.73 and 0.7 is again 0.7. So maximum is nothing but 0.7 and 0.7. So therefore, our fuzzy set A dash is the 0.7 and 0.7. So the scalar cardinality of A dash is 0.7 plus 0.7 minus 1.4. So option is definitely correct. Option B is incorrect because A dash is not normal. Option C is incorrect because it says that the membership of X1 and X2 in A dash are not same. However, membership of X1 and X2 in both in A dash are same. It's equal to 0.7. So option D is correct. Okay. So given a fuzzy if-then rule, you can construct a relation R, and that R captures the conditionality expressed by that fuzzy if-then rule. And this construction of R depends on a fuzzy implication I. Now, given a input fuzzy set A dash or given an antecedent fuzzy set A dash, you infer the consequent fuzzy set B dash by performing A dash composition with R. And given a consequent fuzzy set B dash, you infer an antecedent fuzzy set A dash by performing the composition R with B dash. Okay, so it's not difficult to remember, right? Now, we have seen generalized modus ponens, generalized modus tollens. So the next natural thing to consider is generalized hypothetical syllogism, which is nothing but fuzzy translation of classical hypothetical syllogism, which tells you that if you have P imply Q and Q imply R, from there you can infer P imply R. That's in a sense, it's kind of a transitivity, right? If you think about it. Anyway, so translation of this scheme in fuzzy setting would be you have two fuzzy if then rules. If X is A, then Y is B, and if Y is B, then Z and C, where variables X, Y, and Z take values in universe capital X, capital Y, and capital Z respectively. And these fuzzy sets A and B, A, B, and C are fuzzy sets over X, Y, and Z respectively. Now, from given these two fuzzy if then rules, you want to infer if X is A, then Z is C. Now the question is when do we do that, right? So towards that end, we will make a few observations. Now let us consider the first fuzzy if then rule. If X is A, then Y is B. Then we know that the conditionality expressed by this fuzzy if then rule can be captured by a relation R1, which is a relation which is a fuzzy relation from universe X to universe Y, and it is obtained in this manner. You take the outer product of A and B, and this outer product is based on some implication I. Similarly, If you consider the second fuzzy if then rule, which is if y is b, then z is c, by a fuzzy relation R2, and this fuzzy relation is from universe Y to universe Z, right? Because what is the antecedent universe here? It is Y. And what is the consequent universe here? It's Z, right? And again, this is how you compute R2. It's the outer product of B and C, where outer product is based on implication I. So you have relation R1 and you have relation R2, and these two relations expresses the conditionality between variables X and Y and Z respectively, right? As expressed by fuzzy if-then rules. Now, if you compose these two fuzzy relations, and it is possible to compose them, right? Because R is a fuzzy relation from X to Y and R2 is a fuzzy relation from Y to Z. So if you compose these two fuzzy relation, you'll get a fuzzy relation from X to Z. And this would express the conditionality between variable X and variable Z. After all, R1 expresses conditionality between variable X and variable Y, and R1 expresses the conditionality between variable X and variable Y, and R2 expresses the conditionality between variable Y and variable Z. So if you compose them, if you perform the Maxi composition for some T norm I, you will end up getting the conditionality between variable X and variable Z. But what we want to infer is this, right? This is what we're interested in inferring. If X is A, then Z is C. Now, this fuzzy rule expresses a conditionality between variable X and variable Z, right? And that conditionality is expressed by some fuzzy relation from X to Z. Let us call it fuzzy relation R, right? And how that R will be computed? It will be computed by taking the outer product of antecedent fuzzy set A with consequent fuzzy set C. So we have two relations from universe X to universe Z that captures the conditionality between variable X and variable Z, namely this composition relation R1 composed with R2 and this relation R. So this inference is possible if these two relations R1 composed with R2 and R are consistent with each other, or in other words, they are equal to each other, right? Only then it is meaningful to infer this, right? So we say that from this two fuzzy if then rules, one can infer the fuzzy if then rule if X is A then Y, if X is A then Z is C, if and only if R1 composed with R2 is equals to R, where R1 is derived from first fuzzy if then rule, R2 is derived from second fuzzy if then rule. Their composition expresses a conditionality between variable X and variable Z. And R is the conditionality between variable X and variable Z as computed by this rule, if X is A then Z is C. So if these two relations happen to be equal, then we say that generalized hypothetical syllogism holds, right? So by the way, relation R1 composed with R2 being equal to R is equivalent to saying this, right? That the outer product of A and B composed with outer product of B and C is same as outer product of A and C, right? So in other words, we say that the generalized hypothetical syllogism, if X is A, then Z is C, holds if and only if the composition of R1 and R2 is equals to R. Okay. Now notice that we have two fuzzy connectives at play here. First one is a T norm I, which is used to perform the composition. And you have a fuzzy implication I that is used to build all R1, R2, and R3, and R in fact, sorry, right? And therefore, whether GHS hold in a particular situation depends on this T norm I and fuzzy implication capital I. It may be the case that for a particular choice of T norm I and fuzzy implication capital I, GHS hold, and for some other choice, it may not hold, right? So the fact that GHS holds is contingent on the T norm I and fuzz implication capital I used. Okay, so let us quickly do a problem based on this. We have three universe, X, Y, and Z. All three of them are finite, and you have two fuzzy if then roots. If X is A, then Y is B, and if Y is B, then Z is C, where A, B, and C are given in this manner. And we're required to check if JHS holds, if minimum T-norm along with Gödel implication is used, and if minimum T-norm with Kleene-Diens implication is used. Okay, so I'll quickly recall the definition of Gödel implication in case you forgot. And I hope that I don't need to recall the definition of minimum T-norm. It's essentially minimum of A comma B, right? Now, let us compute the relation R1, right? So that is this, right? The outer product of A and B, and here this implication is the Gödel implication. Okay, so you have 0.1, 1.6, right? And you have performing this. So what will be this Gödel implication? It will be 1.4, 1, again 0.4, 1, 0.4. Okay, and what will be R2? R2 will be outer product of B and C. So this will be 0.2, 1, 0.2, 1, right? Okay. Now let us compose. And for this, we will use minimum T-norm, right? Because that's what we are given. So minimum, right? This is 1. This is 0.2, 0.2, and this is right. And now let us compute the relation R, which expresses the conditionality between A and C, and that is done using this. So we'll have 0.5, 1.6, right? So 0.5 less than, so this is 0.2, this is 1, this is 0.2, this is 1, this is 0.2 again, because 0.6 is strictly greater than 0.2, and this is 1 again. And this happens to be equal to R1 plus R2. So therefore, GHS holds if we use the minimum T-norm and the Gödel implication. So option A is correct and option B is incorrect. Now you can do the same thing to see if GHS holds for when we use minimum T-norm and Kleene-Diens implication. So the Kleene-Diens implication is given like this. Right. So I leave it as I leave this as an exercise. Do it yourself. Homework. Okay. All you got to do is compute the relation R1 and R2. R1 is obtained by taking the outer product of A and B. R2 is obtained by taking the outer product of B and C, do the composition, and see if this composition is equals to R, which is nothing but the outer product of A and C. Okay. And of course, here you need to take outer product with respect to the Queeny-Dayens implication, and the composition will, of course, has to be done with respect to minimum T norm, or in other words, you have to do maximum composition. Okay. So let's take a stock of what we have done so far. We talked about generalized modus ponens, right? And then we talked about generalized modus tollens, and then we talked about hypothetical syllogism. And we started this discussion with generalized modus ponens, right? And I mentioned that there are two broad ways to realize generalized modus ponens, or to basically do generalized modus ponens. The first one is compositional rule of inference, which was proposed by Jede in 1973, and that is what we discuss. That is what we have done so far. So the generalized modus ponens and generalized modus tollens that we did is based on compositional rule of inference. And to just recall, compositional rule of inference involve expressing the conditionality that is given by the fuzzy if-then rule using a relation R, which is a fuzzy relation from antecedent universe to consequent universe. And given a antecedent fuzzy set, you can infer consequent fuzzy sets, or given a consequent fuzzy set, you can infer an antecedent fuzzy set by doing uh, pre-composition or post-composition with this relation R, right? So that is what compositional rule of inference is. Now, the second paradigm to achieve generalized modus ponens is what is called as similarity-based reasoning. So we will now discuss this. So in similarity-based reasoning, the goal is again same. You have a if-then rule, and you have an antecedent fuzzy set A dash, and you want to infer a consequent fuzzy set B dash. Now, in similarity-based reasoning, what we do is the following. Given the antecedent fuzzy set or the input fuzzy set A dash, I compare it with the fuzzy set A, which is the fuzzy set present in the if-then rule, and I compute a similarity value S, which is some number in the unit interval, right? So I compute how similar A dash is to A, or how, to what extent A dash matches A, right? So we compute this value S. That tells me that. That tells me to what extent A dash and A match, or A dash and A are similar, or how compatible A dash is to A. Now, having computed that similarity value S, I use that similarity value to modify the consequent fuzzy set present in my fuzzy if-then rule, right? And what we get as a result of this modification is B dash, our inferred consequent fuzzy set B dash. So given an input A dash, we compare it with the input fuzzy set in our fuzzy if-then rule. That is, we compare A dash and A. I end up getting a similarity value, and that similarity value is used to modify B to get B dash. Okay. Now, the question is, what exactly this similarity value mean, right? So it basically tells you to what extent A dash matches A. And therefore, we can take A dash, the similarity value S, to be the degree of overlap between A dash and A. It can also refer to what extent A dash is included in A, or in other words, the degree of inclusion or subsethood of A dash in A. So suppose my fuzzy set A looks like this, and my fuzzy set A dash looks like this. I should be a bit careful here because the fuzzy set does not have a crisp boundary. So fuzzy set A will definitely not look like this. So for a moment, assume that these are crisp sets, A and A dash. Now, if they are disjoint, that is, they don't share any overlap, then it is safe to say that A dash and A are not similar at all. However, when we have A and A dash sharing an overlap, then it, intuitively speaking, it makes sense to say that A and A dash are similar to some extent. And when A and A dash completely overlap, then it makes sense that they're completely similar, or they're similar to extent one, right? So the idea is that the similarity value S, which is supposed to capture how well ADAS matches A, can be taken to be as the degree of overlap between ADAS and A, or it can also be taken as the degree of inclusion of ADAS in A, right? Or in general, S is a measure of compatibility of ADAS to A. It tells you how well ADAS matches A. Now the question is, given fuzzy set A dash and A over universe capital X, how do we compute the degree of overlap, right? That is something that we need to answer. And similarly, how do we compute the degree of inclusion or degree of subsethood of A dash in A? So we'll quickly answer these two questions and then we will move ahead. So given a universe X and crisp subsets A and B of X, when do we say that A and B overlap? When when their intersection is non-empty, right? Or if we translate this in logical terms, A and B are said to overlap when there exists an element in the universe X such that X belongs to A and X belongs to B. So if instead of having crisp sets A and B, we had fuzzy sets A and B over X, and we wanted to compute to what extent A and B overlap, then we can arrive at a formula for that by looking at what happens in the classical setting and then fuzzifying it. That's exactly what we do. Given a universe X and fuzzy sets A and B over X, the degree of overlap between A and B is denoted by this overlap A comma B, and it is defined by this formula. So it's supremum of minimum of mu A X comma mu B X, where X varies over your entire universe. And this is fuzzification of the classical formula. So X belongs to A becomes mu AX, X belongs to B becomes mu B X. We have a conjunction, so that becomes minimum. You could have taken again uh, any other Tino, but I'm taking the minimum Tino, as is the case. And the existential quantifier there exists translates to supremum, right? And this quantification is the domain of quantification is our universe X, so therefore we take supremum over X. And if you notice carefully, this formula is nothing but height of A intersection B, where this A intersection, by A intersection mean B, I mean the standard intersection, standard fuzzy intersection of A and B. That is intersection based on minimum Tino, right? So the overlap of fuzzy set A and B is given by this formula, right? So you basically look at if this is your A and this is B, uh, you look at this overlap region and you find the maximum membership in that particular region, right? Or basically the height. Okay. And in literature, this overlap formula, this basically this way of computing how similar or how much overlap there exists between fuzzy sets A and B has been referred to as Jadet's maximum measure of similarity. Of course, because it was proposed by Jadet. Now let us see how we can compute the degree of inclusion between two fuzzy sets A and B defined over some universe X. Now let us look at the definition that we are already familiar with. It has already been defined in the class that if we have two fuzzy sets A and B over universe X, we call A to be a subset of B if the membership function of A is always less than equal to membership function of B. But as I discussed in the very first discussion session, that this is a very restrictive definition. This is a very restrictive notion. Why? Because it tells you that if you give me two fuzzy sets A and B, it is either the case that A is a subset of B, or it is not the case that A is a subset of B, right? Because it is based on this inequality. Even if this inequality is violated for one particular X naught, you will be forced to say that A is not a subset of B. But this is very antithetical to the spirit of fuzzy set theory. Because in fuzzy set theory and fuzzy logic, we do things to an extent, right? Therefore, it makes sense to us To what extent a fuzzy subset a fuzzy set A is a subset of fuzzy set B, instead of simply answering that A is a fuzzy subset of B or A is not a fuzzy subset of B. Now, you have already seen a formula for this degree of subsethood or this degree of inclusion. Namely, that if you give me two fuzzy sets A and B over universe X, the degree of subsethood of A and B, which is denoted by this symbol, is 1 if your A is empty set, that is the membership function of A is identically 0, and otherwise it is equals to this ratio, scalar cardinality of A intersection B divided by scalar cardinality of fuzzy set A, right? But this formula actually holds for finite universe only, because in order to compute scalar cardinality of fuzzy set, you are required to do this summation. And this summation exists or converges if X is finite. In certain cases, if your membership function happens to be of this particular form, then this summation would exist even if X is infinite. In fact, in first discussion session, we took one such example where X was our set this and the membership of function looked like this, right? But this was a very sort of artificially constructed example, right? In general, the scalar cardinality of a fuzzy set, which is expressed by summation over the entire universe, almost always does not exist if your universe X happens to be infinite set, right? So that is why this formula is used in the context when your universe X is finite, right? Now the question is, what if the underlying universe is infinite? How do we compute the degree of subsethood or degree of inclusion in such a setting? So we again go back to the classical setting for inspiration. Suppose your universe is capital X and you have two fuzzy sets, two crisp subsets A and B of X. Then when do we say that A is a subset of B? When for every element X of the universe, if it so happens that X belongs to A, then it is necessarily the case that X belongs to B. This is the definition of A being a subset of B, where A and B are crisp sets. Now we fuzzify this formula to obtain the formula for degree of inclusion of fuzzy set A and fuzzy set B. So given a universe X and fuzzy sets A and B, the degree of inclusion of A and B is defined by this formula. Now take a moment to recognize that this is nothing but fuzzification of this. X belongs to A becomes mu AX, X belongs to B becomes mu BX. You have an implication here, so therefore you put a fuzzy implication I, and then you have universal quantification, so that becomes infimum, and the domain of quantification is X. So you have infimum over X, right? So given a universe X, and fuzzy sets A and B over X, the degree of inclusion of A and B is given by this formula for some fuzzy implication I. So if you vary your fuzzy implication, you will get different degree of inclusions, but all of them give you a broad sense to, all of them will give you an extent to which A is contained in B or A is included in B or A is a subset of B, right? The degree to which that happens. Now, we already have seen the Jadet's definition of when a fuzzy subset A is called a subset of some fuzzy subset B, right? So this definition was proposed by Jade, right? And we have already seen that this is a restrictive definition, right? But it's a definition that is used nonetheless, right, in many settings. So it is natural to expect that if A is a subset of B in Jade's sense, that is, the membership function of A is always less than equal to membership function of B. If A is a subset of B, that is the membership function of A is always less than equal to membership function of B, then this inclusion degree should be equal to 1, right? And why it is natural to expect this? Because this Jadais definition tells you that the membership of function is always going to, the graph of membership function of A is always going to lie below the graph of membership function, graph of the membership function of B. So if your B looks like this, your A has to look like this or like this. So intuitively speaking, it seems that A is completely included in B, or degree of inclusion of A in B is equals to 1. Right? So this is a very natural expectation that if A is a subset of B in Jadais sense, then inclusion degree of A in B should be 1. But it turns out that this is not the case. This is not the case for all fuzzy implication. Now, remember that an inclusion, this inclusion measure is based on a fuzzy implication, right? So it tells you, basically it happens, it is the case that if you take an arbitrary fuzzy implication I, then this condition is not satisfied, this condition that we naturally expect to hold. In fact, you can quickly construct a counterexample. Suppose your universe is the entire real line, and you take two fuzzy subsets A and B. This fuzzy set A and B are very simple in the sense that any real number x belongs to fuzzy set A with membership 0.3, and any real number x belong to fuzzy set B with membership value 0.5, right? And therefore, for all real number x, it is the case that membership function of A at x is less than equal to membership function of B at x. Or in other words, A is a subset of B, right? So this definitely holds. Now let us compute the inclusion degree of A and B. This would be infimum as x varies over the universe capital X, and that capital X is R in this case. So infimum of x over R. This is same as infimum, but we are taking the Reichenbach implication. So this becomes 1.1 minus 0.3 plus 0.3 times 0.5. So 0.7 plus 0.15, or in other words, 0.85. So infimum or as x varies over R of 0.85. And that is nothing but 0.85, and that is not equal to 1. Right? So this natural expectation that we have, it turns out that it does not hold in general, right? Certainly not for all fuzzy implication psi. So then it makes sense to ask for which fuzzy implication psi this happens. That when A is a subset of B in Jadais sense, the inclusion of A is completely included in B, or in other words, the inclusion degree of A in B is 1. And it turns out that if I is an R implication, then this happens. So the reason why I included this slide is to give you yet another reason why R implications are nice. Because if A is a subset of B in Jadais sense, then inclusion degree of A in B is 1 if you are using an R implication to define your inclusion measure, inc. So convince yourself that this is the case. This is homework, right? Again, it's not very difficult. All you got to remember is that if this is an R implication, then I of alpha comma beta is 1 if alpha is less than beta, right? This happens for any R implication. I think I have already discussed this. Using this fact, you can quickly prove this. So take this as a homework, right? So yeah, this serves as another reason why R implications are important. So let's go back to the similarity-based reasoning. The first step in similarity-based reasoning is that given the input fuzzy set A dash, we compare its similarity value with A, which is the input, which is your antecedent fuzzy set in the fuzzy extent rule. Now, the question that we were faced with was how to compute the similarity value S. We already know how to do that. We have an overlap measure and we have an inclusion measure. So first step is taken care of. What about the second step? That is, how do we modify our consequent fuzzy set B using this value S to obtain B dash? Now, multiple methods have been proposed for this. I will discuss a couple of methods which are the most important ones. First method is called as first method is referred to as membership value reduction, which is defined in this particular manner. That the membership function of B dash is given by multiplying the similarity value S with membership of Y in B. And notice that this is well defined, right? Because S comes from the unit interval. This comes from unit interval. So when you take their product, what you get is also a member of the unit interval. So this indeed is a well-defined membership function, right? And why is it called membership reduction? Because given the membership value of Y in B, which is some number in the unit interval, when you multiply S with it, you actually end up getting a number that is smaller than mu by, right? So in that sense, you are reducing the membership value of B, membership value of Y in B to get the membership value of Y in B dash, right? So one thing to notice, so that is why we have this term membership value reduction or MVR in general. One thing to notice about this way of obtaining B dash is that although the membership values are getting reduced, the overall shape of the fuzzy set B stays intact. So if the shape of the membership function of B stays intact. So if our B was a triangular fuzzy set, S times B is going to be again a triangular fuzzy set. So it will probably look like this, B dash. If our B looked like this, B dash is going to look like this, right? Or maybe I think it will be elongated. So the point is MVR. So this particular way of obtaining B dash ensures that the shape of B dash is same as B. Okay. Now, if you were a bit careful, you would recognize that we are essentially performing the product operation between S and mu by in order to get mu b dash y. But product operation is a specific example of minimum of T norm, right? Product is an example of T norm. So we could have taken any T norm I, right? So more generally, I would obtain mu b dash of y by computing I of S comma mu by, right? So this is the first way of obtaining the output fuzzy set B dash in similarity based reasoning. You first compute the similarity value S, and then you modify your consequent fuzzy set B in this manner or using a arbitrary T norm I. So generally, when I use the term MVR or when the term MVR is used, we are referring to this particular formula. And if it is specifically specified that we are using MVR based on T norm product T norm, or if it is specifically specified that MVR based on drastic T norm or on Lukacs on bounded sum T norm is used, then in that case we use this formula. But MVR by default refers to obtaining B dash by multiplying membership function of B with S. Okay, so this is the first way of obtaining uh, of obtaining output fuzzy set B dash in similarity based reasoning. Let us look at another way. This is called as more or less or ML in short. It says that having obtained the membership value S, you obtain the having obtained the similarity value S, you obtain the membership value B dash, the membership function B dash like this. So you compute the membership value of Y in B, you divide it by S, and then you take the minimum, right? So this may not look very straightforward, right? But I hope I'll be able to convince you that there is a very good reason for defining B dash in this manner. So if you again, if you were a bit careful, you would recognize that this is nothing but Gogun implication evaluated at S and mu by. So recall, how is Gogun implication defined? It is 1 if A is less than equals to B, and it is B by A if A is strictly greater than B. And it turns out that this is nothing but minimum of B by A if A is greater than 0, and it is, uh, I think, 1, right? Because, yeah. So Gogol implication, which is defined in this manner, generally defined in this particular manner, can also be expressed in this particular form. Okay. So in other words, this mu b dash, which is defined in this particular manner, is nothing but Gogon implication at s comma mu by. Of course, here I'm assuming that your similarity value s is greater than 0, right? Uh, which is almost always the case, right? Because if you have a fuzzy if then rule, then you're going to use it in a case when your input fuzzy set A dash is actually similar to A. If your fuzzy if then rule says that if tomato is red, then it is ripe, then you won't apply it for apples, right? But therefore, I'm assuming that S is greater than 0. If S is not, if S is actually equal to 0, then we won't consider this more or less way of obtaining B dash, right? So this holds when the similarity value is S greater than 0. Okay. Anyways, so this is how the formula for mu dash is given, and we make the observation that it is nothing but Gowan implication at S comma mu by. Now the question is why this term more or less is being used, right? Now, in order to see that, suppose your fuzzy set B was 1, 2, and 3, this triangular number 1, 2, and 3, and your similarity value turns out to be 0.6. I'm just using this set and this for similarity value for the sake of illustration. So this is how our fuzzy set B would look like, and this is 0.6. So what will be this value? This will be 2 minus 0.6. So this would be 1.4, I suppose. So what will be the equation of this thing? It will be 2 by x. This is 1.4 and this is 2.4. Okay. So I hope I am not committing an error here. So x minus 1 by 2 minus 1 is equals to 0.6. Okay, so this is 1.6, my bad. It looked that it's not certainly not 1.4. Okay. So this is our fuzzy set B, and this is our membership value S, right? Now, what would be the formula of fuzzy set B dash? It's minimum of this thing. In other words, it's equal to mu b of y divided by zero point 0.6 if is less than equals to 1, or in other words, mu by is less than equals to 0.6, and it is equals to 1 if mu by 0.6 is greater than 1. And what is 1 divided by 0.6? It's 10 by 6, or in other words, 5 by 3. And this we know that if y is between 1.6, 2.4. So given a fuzzy set B and a similarity value of 0.6, mu b dash computed using this formula turns out to be this. Now, what exactly this definition tells us? It tells us that if the membership of y in B is greater than 0.6, then the membership of y in B dash is 1, right? And if it is less than 0.6, then this membership value is scaled, right? Scaling factor is 5 by 3 in this case, right? So what you end up getting as B dash looks like this. So maybe I will draw that fuzzy set here only. So for any y between 1.6 and 2.4, or for any y that belongs to B with a degree that is at least 0.6, it belongs to B dash with membership 1. And for any y that belongs to B with membership less than 0.6, it belongs to B dash with a membership that is scaled, that is 5 by 3 of mu B of mu by. That value is increased, right? Because 5 by 3 is of course a number greater than 1, right? So in other words, we are essentially saying that if the membership value mu by right, right. Now consider the wake concept more or less 0.6. Consider the wake concept more or less consider the wake concept membership is more or less 0.6. Then any membership that is greater than 0.6 definitely satisfies this concept with a degree 1, right? And any membership value that is slightly lower than 0.6 satisfies it to a greater degree, to a degree like that's closer to 1, certainly not equal to 1, but somewhat closer to 1. So it's, or basically it's a high value, right? So in other words, membership of y in B dash, which is defined in this particular formula, is the degree to which this membership value mu by is more or less s, right? So the concept of more or less 0.5, which is a vague concept, is what this formula captures. So take a moment to recognize this. It may not become very immediate in one go, but think a little bit about what I said. Membership of y in B is mu by, right? Membership of y in in B is mu by. Then consider the wake concept. More or less S, right? It's a wake concept. The number zero point 0.6 is a crisp number, it's a real number, but more or less 0.6, it's a wake concept. And the membership of mu by in this wake concept is what gives us mu b dash y. So in other words, this is why the term more or less used. I could have simply given you the formula for this particular formula and asked and could have solved a couple of problems. But I wanted to give you an intuition why this is called more or less in literature. If you look at books or research papers, you'll find this term being used. So I wanted to give you a sense of why that is the case. Okay. And of course, you could have said that why use Gogon implication here? I could use any fuzzy implication, right? So you can of course do that. But when the term more or less used without an explicit reference to a fuzzy implication, this is what you are required to use. In a similar way, when MVR is used without any explicit reference to a TNOM, you have to use product operation. Okay. So let us quickly summarize what we have done. In similarity-based reasoning, given a fuzzy if-then rule and an input fuzzy set A dash, you compute the similarity value of A dash with fuzzy set A, which is the antecedent fuzzy set in the fuzzy if-then rule. Having obtained this similarity value S, you use that to modify B, which is the consequent fuzzy set in your fuzzy if-then rule, and this modification gives you the output fuzzy set B dash. There are two ways to obtain the similarity value, or at least we discussed two ways to do that. First one is the degree of overlap, or what we refer to as overlap, a a dash comma a, and then the other method is degree of inclusion of a dash in a, which we denoted by inc a dash comma a. And having obtained this similarity value s, we modify b using s to obtain b dash, and there are two ways to do that. First one is MVR, membership value reduction, where you use the product operation or more generally a TNOM I. And the second is more or less, which is based on Gogon implication by default, but you can use any TNOM, any fuzzy implication I. Now let us solve a problem. We have variable x and y. We have fuzzy set A and B. This is our fuzzy if then rule, and we are given a fuzzy set A dash over universe X, and we are required to infer the output fuzzy set B dash using similarity based reasoning, or SPR in short. Now, this in order to actually use similarity based reasoning, we first need to specify two things. First one is what similarity measure are we going to use to compute S, and what modification scheme we are going to use. So this question by itself does not make sense unless these two things are specified. Now, suppose I specify that ZA's maximum similarity and MVR modification scheme is to be used. Then let us solve this problem. And notice that when MVR modification scheme is specified, we will use the product operation. Okay. So this is our A dash, our input fuzzy set, and this is our A, the antecedent fuzzy set in the if then rule. So we'll compute the similarity value S, which is the overlap of A dash in A, or in other words, the height of A dash intersection A. And what is the intersection of A dash and A? So we take the minimum, right? Because this is a standard intersection. So minimum of 0.5 and 0.7 is 0.5, minimum of 0.2 and 0.9 is 0.2. So what is the height of this fuzzy set? It's 0.5. And then having obtained the similarity value, we obtain our fuzzy set B dash by MVR scheme, which uses the product operation by default. So in other words, the membership function of B dash looks like this. right? So in other words, B dash is uh, 0.5 multiplied by 0.5, 0.5 multiplied by 0.3, okay? So this is what you get your as your output fuzzy set when ZA is maximum similarity and MVR modification scheme is used to perform similarity-based reasoning. So I hope you got a sense of how to solve problems based on SPR. Okay, now let us use something else as our similarity measure. Suppose I use the Ukashevich implication-based inclusion measure and MVR modification scheme based on IM. So instead of using the product operation, I'll use the minimum operation and solve the exact same problem. Okay. So what will be inclusion degree of A dash in A based on Ukashevich Tino? So just to recall, Ukashevich implication is given in this particular manner, right? So this is right. And since here our X consists of only two elements, this is nothing but right. Now this is zero point 0.5, this is 0.7, right? This is 0.2 and this is 0.9. So what is Ukashevich implication evaluated at 0.5, comma 0.7? So 1 minus 0.5 is 0.5, 0.5 plus 0.7 is 1.2, then minimum of 1 and 1.2 is 1. And what is Ukashevich implication evaluated at 0.2 and 0.9? So 1 minus 0.2 is 0.8, 0.8 plus 0.9 is 1.7, and the minimum of that is 1. Okay, so ADAS is included in A with degree 1 when the inclusion is computed using the Ukashevich Tino. Now let us now evaluate our output fuzzy set B dash. That is given in this particular manner because we are asked to use MVR modification scheme based on IM. IM is the minimum operation. But our similarity value is 1. And minimum of 1 comma membership value of Y in B is nothing going to be membership value of Y in B. In other words, our output fuzzy set B dash happens to be B only, which is basically this fuzzy set. Okay. So we have uh, saw how similarity based reasoning works, right? How generalized mode exponents based on similarity based reasoning works. Now I will talk about a specific similarity based reasoning scheme, which is called as Mamdani inference scheme, right? And this is basically what is the central focus of the course. So Mamdani inference scheme was proposed by this person named Mamdani, an engineer who, by the way, did his early education in India only. And he proposed this scheme in 1977. And this Mamdani inference scheme is nothing but GMP based on similarity based reasoning, where ZA's maximum similarity measure is used and MVR modification scheme based on minimum T norm is used. Remember, MVR modification scheme involves product operation by default, but we can use any tnorm instead of product operation. And if we use the minimum tnorm and we use JDA's maximum similarity measure as our way to compute similarity value S, then what we end up getting is nothing but Mamdani's inference scheme. So let us see how it turns out. Suppose I have this fuzzy if then rule. If X is A, then Y is B, where you have universe X and universe Y. And this is where the variable X and variable Y take values in. A is a fuzzy set over X and B is a fuzzy set over Y. And suppose we are given an input fuzzy set A dash. So we first computed similarity value. We compute how similar or how well A dash matches to A. And for that, we use the ZA's maximum similarity measure. That is this particular formula. Having computed this S, we infer our output fuzzy set B dash by modifying B. And how is this modification done? Using MVR modification scheme, but based on minimum T norm. That is, this is how the membership function of B dash looks like. And if you substitute the expression for S, you'll get this, basically this formula. Okay. Now, what is uh, okay? So there's something very interesting about Mamdani inference scheme, but I'll come to that in a short while. Let us first quickly do a problem. So this is the same setup that we had before, but here we are required to use Mamdani inference scheme. So let us first compute the similarity value S, which is max min. Uh, and here I'm not using the supremum because, of course, our universe X is finite. So supremum is same as infimum. Right? And this is nothing but height of A dash intersection A. And we have already seen that this height is 0.5, right? Because minimum of 0.7 and 0.5 is 0.5, minimum of 0.9 and 0.9 and 0.2 is 0.2, and maximum of 0.5 and 0.2 is 0.5. So similarity value is 0.5. And we have to use the Mamdani inference scheme, and therefore I will use minimum operation to perform the modification operation. Uh, just a minute. Okay. So this is nothing but minimum of 0.5 comma mu by. And therefore, B dash would be the membership of Y1 in B dash is minimum of 0.5 with 0.5. So this is 0.5. Membership of Y2 in B dash is minimum of 0.5 and 0.3. So it's again 0.3. Membership of Y3 in B dash is minimum of 0.5 and 0.7 to 0.5. Okay. So Mamdani inference scheme is just an instance of similarity based reasoning where we use the Jaday's maximum similarity measure, or in other words, we take the height of A dash intersection A and we use the minimum T norm to perform the modification step. Okay. Now, I just want to make an observation here. When we talked about MVR modification scheme, this is what we discussed, right? The default MVR modifications scheme. And there I made a comment that this way of obtaining B dash from B preserves the shape of B. So if your B is triangular fuzzy numbered, then B dash would also will have a triangular shape. Similarly, if B had a Gaussian shape, then B dash would also have a Gaussian shape. However, when you take the minimum, instead of using the product operation, you use the minimum operation, like we do in Mamdani inference scheme, you actually distort the shape as well. So if your B looked like this and S is somewhere here, then when you take the minimum of S and B, you actually end up getting this. In other words, you do a clipping. You clip the fuzzy set B. This has the effect of clipping B. And therefore, when you use Mamdani inference scheme, you actually end up distorting the shape of your fuzzy set B. Or in other words, the shape of fuzzy set B dash is a distorted version of B, of shape of B. So I just wanted to make that point. So that is the difference between MVR modification scheme based on product operation and minimum operation. In product operation, the shape of B dash is same as shape of B, while in minimum operation, when we use minimum operation to perform this modification, the shape of basically you clip B in order to get B dash. Anyways, now comes the interesting part. We have started our discussion on generalized modus ponens from compositional rule of inference. Now, interestingly, Mamdani inference scheme can also be seen through the lens of compositional rule of inference. And I'll show you how. So in compositional rule of inference, this is what we do. We have a fuzzy if-then rule. Then from that, we build a relation R that captures the conditionality expressed by this rule. And we build this relation R using a fuzzy implication I, right? So that's what we do in compositional rule of inference. This relation R is built using a fuzzy implication I, namely in this manner. You take the outer product of A and B. And then given an input fuzzy set A dash, you infer your output fuzzy set B dash in this particular manner. Now, suppose instead of using a implication I to build your fuzzy relation R, you use the minimum T-norm operation. In other words, instead of having an implication I here, you use the minimum operation. Okay. And then let us infer our output fuzzy set B dash given input fuzzy set A dash. And by the way, this way of building R using minimum operation essentially gives us the Cartesian product of fuzzy set A and B. So if you remember our discussion session in which I discussed the extension principle, I talked about given two fuzzy subsets A and B, given two fuzzy sets A over X and B over Y, I can compute the Cartesian product of A and B. And that happens to be a fuzzy set over X cross Y. And the membership function of this Cartesian product is nothing but this. And in that particular session, I explained in detail why this is the case. So if you are having if you're suspicious about this formula, I would encourage you to go back to that discussion session and like understand why Cartesian product is of fuzzy sets is defined the way in which it is defined. So, anyways, in Mamdani, so instead of building our fuzzy relation R using a fuzzy implication, I'm using the minimum operation to build that. And it turns out when you do that, then R is nothing but the Cartesian product of A cross B. Okay. So instead of taking outer product of A and B, you are just taking the Cartesian product. And then let us infer the output fuzzy set B dash given the input fuzzy set A dash. What will be the formula for that? It will be nothing but this, right? We have already seen the formula, right? This formula is something that we have already seen. So I hope you don't have any problem with this, right? Now let us substitute the formula for mu r. Remember, r is built using the minimum operation. So this is what we will get. Okay. So this is nothing but mu r of x comma y. Now let us look at this whole expression. We are taking the minimum of mu a x and mu b y, and whatever value we get, we are taking that minimum with mu a dash x. So in other words, we are taking minimum of these three values, mu a dash x, mu a x, and mu b y. But minimum operation is associative. So instead of taking minimum of these two values first and then taking its minimum with this, I could take the minimum of these two values first, and then I can take whatever we get, minimum of that value with mu by. So in other words, I can write this exact same formula in like this. Okay. Now we are taking the supremum of this quantity as x varies over universe capital X. And this value, the second value in our outer minimum, depends only on y. So it makes sense that it seems reasonable to send this supremum, which is lying outside this bigger outer minimum operation, inside, right? And it turns out that you can actually do that. This is mathematically justified. I'm not going to prove why that is the case. It's slightly non-trivial, but take it as an exercise to do that. Right? Prove that this whole supremum is nothing but this. Right? That is, you can take the supremum that is lying outside inside the minimum, inside the outer minimum. And when you do that, you get this. But supremum of minimum of mu a dash x comma mu a x, where x varies over universe capital X, is nothing but your similarity value S, right? That's Jadet's maximum similarity measure. So what you get is S. And then you are taking minimum of S comma mu by. Now this is nothing but Mamdani inference. So in other words, Mamdani inference scheme, which we defined as a specific example of similarity-based reasoning, can also be looked from the lens of compositional rule of inference. The only difference is here you build your relation R using the minimum operation instead of a fuzzy implication, right? And it is reasonable to question that, okay, mathematically it makes sense, right? We have shown that when you build your relation R using minimum operation, then your what you end up getting is uh, uh, what you actually end up getting is basically the Mamdani inference, right? But does it make sense to build our relation R using minimum operation, right? Because I have said this so many times that the fuzzy relation R captures the conditionality which is expressed by this fuzzy if then rule, right? So for any particular value of input variable y, and for input variable x, and for any particular value of output variable y, mu rx comma y expresses the strength of conditional relationship between this pair, this input output pair, right? Now, instead of using an implication I, which seems like the logical thing to do, right? Because this conditionality is expressed in logical terms using an implication. But in Mamdani inference, instead of using that implication I, you're using the minimum operation. But minimum captures conjunction or and not the conditionality. Then is it mathematically logical to use such a relation R? And it turns out that it is. I mean, because Mamdani inference has been hugely successful. It's one of the most widely used application of fuzzy set theory. Many devices like washing machine or uh, uh, even air conditioners used use this inference scheme. So this relation R built using minimum operation may not capture the conditionality between variable x and y in a proper logical sense of that term, but it ends up capturing some kind of association between input variable x and input variable y. And it turns out that particular association is enough in many practical examples, in many practical cases, right? Okay. So Mamdani inference scheme can be looked from a classical compositional rule of inference viewpoint, in which case you build your relation R using by taking the Cartesian product of A with B, or in other words, by using the minimum operation. And it can also be looked from a similarity-based reasoning perspective, in which case you compute your similarity value S using the ZA's maximum similarity, and you use that to modify your B in order to get B dash. And in CRI viewpoint, you basically compose A dash with R to get your B dash. Okay. So I hope by now you have a sense of what Mamdani inference scheme is, right? Because it's very important, first of all. As I said earlier, Mamdani inference scheme has been used at so many in so many applications. So this is something that you should definitely learn whenever you are taking a course on fuzzy set theory or fuzzy logic. Okay. Now let us quickly do a problem. Hmm, just give me a second. I will quickly arrange my notes. Um, okay. Now we are given the rule: if the temperature is warm, then fan speed should be high. Where again, it is easy to identify what are the variable x and y here. X is temperature value, and it take values in the universe x, where x is defined to be this thing, minus 20, 50 degrees centigrade. It's the set of all possible room temperatures, set of all possible temperature values. And from looking at x, it seems that the context here is a room. And our variable y is a fan speed, and it take values in set y, which is 0, 600, the interval consisting of 0 to 600 RPM. And our input is here if temperature is moderate, where moderate is this particular fuzzy set. So our A dash is 15, 25, 35, this triangular fuzzy number. And we are required to infer fan speed using Mamdani inference scheme. Okay, so let us plot this first. And by the way, this is our fuzzy set A. I hope you are able to identify that. And this is our fuzzy set B. So this is the antecedent fuzzy set, right? It appears in the antecedent. And this is our consequent fuzzy set. This appears in the consequent part of the if-then rule. So let us quickly plot these two fuzzy sets, A and B. So this is what you get. So this is our fuzzy set A, and this is our fuzzy set B. Okay. I hope you are able to see that. This is both our trapezoidal fuzzy numbers. And they, in fact, they are what are called as degenerate trapezoidal fuzzy numbers, because two of the parameters, more specifically the last two parameters, are same. So what you end up getting is a degenerate trapezoidal number. Again, this is something that I've discussed in a previous session. You are familiar with trapezoidal fuzzy numbers. In case any of the two parameters or any of the three parameters become same, you actually end up getting not a proper trapezoid, but a degenerate trapezoid. Anyways, so this is our fuzzy set A, this is our fuzzy set B. And this is our input fuzzy set A dash, right? So our input fuzzy set A dash is basically moderate, and that is given by this 15, 25, and 35. So let us plot A dash and A together, or in other words, moderate and warm together. We are required to do Mamdani inference scheme. So we will first compute the similarity value S. And how is that computed? It's nothing but height of A dash intersection A, where intersection means standard fuzzy intersection or intersection based on minimum T norm. So if this are our two fuzzy sets, A dash and A, what will be their intersection, their standard fuzzy intersection? It will be this, right? So simply take the minimum of these two graphs. So this is what you get. Or in other words, this is A intersection A. And what is the height of this A intersection A? It's clear that it is 0.5, right? In fact, this is the value of at 30. So, we know what is the similarity value 0.5. Now, having obtained the similarity value, let us modify our consequent fuzzy set B, which is nothing but fuzzy set high, in order to get our output fuzzy set B dash. So this is our output fuzzy set B equals to high. Let us draw the line y equals to 0.5 or y equals to s, and then do the clipping part. So when we clip it, that is when we take the minimum of membership function of high, fuzzy set high with 0.5, you essentially do the clipping. This is what you get. In other words, this is your output fuzzy set B dash. Okay. So I hope you got a sense of how to solve a problem based on Mondani inference scheme. So as of now, this is how our fuzzy inference pipeline looks like. We have a fuzzy if then rule and we have some kind of inference scheme. So this inference can be a compositional rule of inference, or you can have a similarity based reasoning scheme. For example, a Mamdani inference scheme. And you're given an input fuzzy set. You use this inference scheme and this fuzzy if then rule, and you compute your output fuzzy set. Okay, so your input is in the form of a fuzzy set, and your output is again in the form of a fuzzy set. However, usually the input is not in the form of a fuzzy set. The input given to us is not in the form of a fuzzy set, but a crisp value. And the output is also required to be a crisp value and not a some fuzzy set, right? So for example, in this particular question that we just did, it is unlikely that our input, the input that will be given to us, will be some fuzzy set moderate. Instead, we will be given a particular temperature value, and we will be required to produce a particular value as the output, and that value will essentially be the speed at which the fan will be set, right? So in practical situations, your input is not in the form of a fuzzy set, but in the form of a specific value for your input variables. And similarly, it is expected that the output is produced as a number, as a crisp value instead of a fuzzy set, right? So this is achieved by fuzzification of input values and defuzzification of output fuzzy sets. That is, given a particular value for input, I fuzzify it to obtain the input fuzzy set A dash. And similarly, having obtained the output fuzzy set B dash, I defuzzify it to get a output value. Given an input value, I fuzzify it to get input fuzzy set A dash. And having obtained the output fuzzy set B dash, I defuzzify it to get an output value. Now, suppose this is our fuzzy if then rule again, and we have the familiar setup, and we are given a particular input value. So say x, the variable x is equals to x naught. Then how can we fuzzify it? So there exist multiple fuzzification scheme. I'm going to discuss two, the most widely used ones. First one is the singleton fuzzification. Singleton fuzzification, as the name itself implies, means that x naught, your input value, is fuzzified as a fuzzy set A dash. And this fuzzy set A dash take value 1 at x equals to x naught, and at everywhere else it takes the value 0. And that is why it's called singleton fuzzification. You are fuzzifying it at x naught only. You are defining this A dash in a manner that it attains membership value 1 at precisely x naught, and everywhere else it is 0. And then you have something called as triangular fuzzification. So if I were to denote this graphically, x naught translates to a fuzzy set right? It just attains the membership value at one particular point. In triangular fuzzification, given a particular input value, you construct a triangular fuzzy number around it. In other words, your x naught is fuzzified as a x naught b, where your numbers a and b, of course, are in this particular manner. The parameter a has to be less than x naught, and parameter b has to be greater than x naught. And one thing to notice here is that this triangular fuzzification is possible only if your input universe X is a subset of real line, right? Remember that triangular fuzzy numbers are essentially fuzzy sets over real line. If your universe happens to be set of people, for example, set of people in a particular room, then there you cannot define a triangular number, right? A triangular fuzzy number. But in most cases, your input universe actually is a real line or some subset of real line. Okay. However, when you compare it with singleton fuzzification, here you don't require anything, any assumption on the nature of X, right? Here your X can be anything. It could be real line, it could be XY plane, it could be set of people, it could be set of objects, anything. Now, in practical applications, singleton fuzzification is the one that is usually preferred, primarily because, as I said just now, it can be done regardless of the nature of the universe X, and it is computationally inexpensive. It's not a very computationally demanding falsification scheme. And I'll illustrate that. Uh, uh, Now I will illustrate why that is the case. Suppose I using a compositional rule of inference. Then this is how our rule will be modeled, and this is how our output fuzzy set B dash will be obtained, right? Now let us quickly look at the membership function of our output fuzzy set B dash. So we are taking a supremum. Now notice that this supremum can be our x can be written as x naught, singleton x naught union x minus x naught. And therefore we can break this supremum into two parts. Right? So when we are taking supremum x equals to x naught, that is nothing but evaluating this quantity at x naught. Now this is one by definition, right? And this is zero. But minimum of zero comma some number in the unit interval is again zero. This whole thing is zero. And therefore, when you take supremum of zeros, you end up getting zero. So the second term would be zero. And what would be the first term? It is minimum of 1 comma mu r x naught comma y. In other words, it's just mu r x naught comma y. And therefore, this is what you end up getting. Right? So in other words, your membership function of B dash has this nice expression. You don't have to do any supremum, infimum, anything. You'll simply need to compute the membership of x naught in A, and then you compute the implication at that particular value, comma mu by, and that will give you the membership of y in B dash. And therefore, this whole entire computation of supremum is eliminated, thereby suggesting that when you use singleton fuzzification for your input, compositional rule of inference is pretty straightforward. Right? In other words, this is what you get. Similarly, when you use similarity based of reasoning, similarity-based reasoning, and you use singleton fuzzification, this is what you get when you use Jadet's maximum similarity, and this is what you get when you use the degree of inclusion based on some implication I, right? So this entire, so in supremum, when we compute similarity value, we have to perform a supremum operation when we are using Jadet's maximum similarity. That process is completely eliminated. And similarly, when we are using degree of inclusion as similarity value, there we have to perform an infimum operation. That process is also eliminated. And in fact, if you use an R implication, then we know that this essentially turns out to be mu x naught. Another reason why R implications are important, right? So in other words, when you use singleton falsification, your similarity value is basically mu a x naught. Okay. And therefore, you can infer your output fuzzy set B dash either like this, that is when you're using MVR, default MVR modification scheme, or this is the general modification scheme where you use a Tino I, or you can use more or less, or more generally any implication I, right? So the point is, when you use singleton falsification, your inference step, the steps involved in the inference becomes very straightforward. And that is why we say that singleton falsification is computationally inexpensive as a whole. And that is why it is preferred instead of triangular falsification, where you got to do the supremum and infimum, and that is a computationally intensive task. Anyway, so we have discussed how, given an input x equals to x naught, we can fuzzify it. We can do singleton fuzzification or we can do triangular fuzzification. Singleton fuzzification is what is preferred because it's computationally straightforward and it can be done on any universe X, regardless of whether it is real line or some part of it, or it is XY plane, or it is a set of objects and so on. Now the question is, suppose that we have used our inference scheme to infer output fuzzy set B dash. How do I appropriately convert into a output value that we can give to the user? This process is called as defuzzification, as I have already indicated. Now, the question is, how do we do this defuzzification? Again, there are methods available for it. I'm going to discuss two methods, center of maxima and centroid. And by the way, both these methods are applicable when your consequent universe Y is a subset of real numbers. Now, that is again that is very important to remember. But in most practical application, this is satisfied. Your consequent universe Y is either the real line or some subset of it. So enough for almost all practical applications. Okay. Now, um, suppose this is our output fuzzy set B dash, right? Where Y is basically some subset of real line. Then what you do is you look at the height of B dash. Okay. So suppose your B dash is looks like this. It's unlikely that you will ever encounter such a B in a practical situation, but for the sake of illustration, suppose that this is how your B dash looks. Then you first of all compute the height of B dash. That is the maximum membership that your basically the this, by the way, I hope you remember. Right, so it's the supremum of all the values that it can possibly the membership function of B dash can possibly attain. So in this particular case, this is basically the height. Suppose this value is h. Okay. So you first compute the height of your output fuzzy set B dash. Then you look at all the members of the universe Y where that height is actually attained. So this height is attained in this particular case at, say, this is P. No, let's not use P. Suppose this is Y1 and this is Y2. This is Y3 and this is Y4. So the height H is attained on y1 comma y2 union y3 comma y4. And this is what this set M is. It's the set of all members of the universe Y where height is attained, where the membership of Y in B dash is equals to height of B dash. And suppose this set M is bounded. So if you have a B dash that look like this, right? And suppose this is basically height, then this height H is attained, and suppose this is Y naught, this is Y naught, then this height H is attained at all Y greater than equal to Y naught. So in this case, M is not bounded. So we are assuming that this set M, the set of all members of the universe Y, where your height is attained, height of B dash is attained. Suppose this is bounded. Then infimum and supremum of M exist, and then you simply take their arithmetic mean, and that will give you the defuzzified value. That will give you the output value. So in this particular case, the infimum, it's pretty clear, is Y1, right? This is the infimum, and the supremum is Y4. So their arithmetic mean will give you the defuzzified value. So their arithmetic mean will lie somewhere here or here, and that will be the defuzzified value. Okay. So center of maxima defuzzification method is pretty straightforward. Now let us look at centroid method. Now in centroid method, uh, you have the condition that your output fuzzy set needs to have a bounded support. So if you look at a B dash like this, it does not have a bounded support, right? I hope everyone remembers that support of a fuzzy set M. What should I use? Support of fuzzy set B is the set of all values of the universe that belong to set of all members of the universe Y that belong to fuzzy set B with a non-zero membership, right? So this is sort of the interesting part of the universe Y, because in this particular part, you have members belonging to non-zero membership in A, in B, right? So centroid method is applicable when your consequent fuzzy set B dash has bounded support. Okay. Now, in this particular case, in centroid method, your defuzzified value Y is defined as the horizontal coordinate of the centroid of the region under the curve Z equals to basically membership function of B dash within the support of B dash. Again, a mouthful, but let me explain. Suppose this is your B dash, okay? And this value is A and this value B. So support of B dash is A comma B and it is bounded, okay? Now look at the region under the membership. And so what basically this is the graph of membership function of B dash, right? So this is our universe and let us call this is Z. So this is nothing but Z equals to mu B dash of Y, right? So I'm calling the horizontal axis as Y axis because B dash is a fuzzy set over the universe capital Y. So that's why I thought it would be appropriate to use the symbol Y for the horizontal axis. And therefore, I'm calling the vertical axis to be the Z axis. Okay. So support of B dash is A comma B, which is bounded. And this is basically the graph of the membership function of B dash. Now let us look at the region subtended by this graph with the horizontal axis. So this is our region R, right? Now this region R, we can compute the centroid of this region. So suppose centroid of R gives you, so this would be Rx comma Ry. So maybe it says lies somewhere here. And the, okay, sorry. So I should write Y and Z, right? Because we are using Y axis as we are using horizontal axis as the Y axis and vertical axis as the Z axis. So suppose the centroid of R is Ry comma Rz. Then centroid method says that the defuzzified value of the output fuzzy set is nothing but the horizontal coordinate of this centroid. So this is basically Ry. Again, nothing very complicated. You simply plot the membership function of the output fuzzy set B dash on the YZ plane. You look at the region that is subtended by this membership function with the horizontal axis, which is the Y axis, within the support. So this is basically the support of A comma B. And then you compute the centroid. In fact, you don't need to compute the entire centroid. You just need to compute the horizontal coordinate of the centroid, which is basically the Y coordinate. And that will be your the that will be your uh, that will be your defuzzified value. Now the question is, how do you compute uh, this centroid? Now, if you remember class 11th physics, you would recall that the this region centroid can be easily computed, right? And the formula for that is, so the horizontal coordinate of centroid is given by area of the region R with YdA, and RZ is given as ZdA, right? Where dA basically refers to a infinitesimal area element. And if you don't want to get into all these specifics, you can write the straightforward formula. And this is basically the area of the region R. Now, this R is basically the area subtended by the membership function of B dash with the horizontal axis. So the area can be expressed pretty straightforwardly. It's nothing but the integral of from A to B, right? And similarly this. Okay. So the horizontal coordinate of the centroid of region R is basically given by this formula. That is basically, which is what I have written here. Okay. So the centroid method is of course applicable when your output fuzzy set B dash first of all has a bounded support, and also your your membership function of B dash needs to be nice in the sense that this integral should be computable. If B dash happens to be a highly discontinuous function, then you won't be able to compute that integral, right? So your membership function of B dash the membership function of B dash needs to be nice in the sense that we are able to evaluate these integrals. And in almost all applications, you will find such nice membership functions only. But it is useful to recognize that you need bounded support of B dash, you need bounded support for your fuzzy set B dash, and you also need to have nice membership function for B dash. Okay. So having talked about fuzzification and defuzzification, our general fuzzy inference pipeline will now look like this. You have, of course, a fuzzy if then rule and an inference scheme, which could be an CRI or could be SPR. You have a crisp input value, which is fuzzified to obtain the input fuzzy set. You perform your inference using the fuzzy if then rule and the inference scheme. You obtain an output fuzzy set, and this output fuzzy set is defuzzified to produce a crisp output. Okay, so this is how the general inference, fuzzy inference pipeline looks like. Okay, now we have the same question as before, but here now we are given a particular input temperature, input value, namely the temperature equals to 32 degrees centigrade, and we are required to compute the fan speed using, of course, Mamdani inference and with the centroid method. Okay, so this input of 32 degrees centigrade is fuzzified. Nothing is given, so we'll do singleton's fuzzification. This will be 1 when x equals to 32, and everywhere else it is equals to 0. Right? Now we compute the similarity value of S with similarity value S, which is the similarity value between A dash and A. A in this case is 1. This is by the way B. So similarity of between A dash and A is nothing but height of A dash intersection A. And we have already seen when I was talking about singleton fuzzification that this is nothing but mu A x naught. In x naught happens to be 32 degrees centigrade, right? So just to recall, when we have used singleton fuzzification, this entire, okay, so I did not do that. So maybe I'll do that here. In suppose your A dash is obtained by singleton fuzzification at x equals to x naught. In other words, mu ax is 1 if x equals to x naught, and it is 0 everywhere else. Okay, and you have a fuzzy set A, and you want to compute your similarity value between A dash and A using ZA's maximum similarity measure, which is nothing but height of A dash intersection A. So this is nothing but this can be broken into two parts because x is nothing but x naught union x minus x naught. This is 1, and therefore this whole thing turns out to be mu x naught. This is 0 because x varies over x minus x naught, and for all x uh, equal x, for all x not equals to x naught, membership of x in A dash is 0. This is 0, therefore the entire minimum is 0, and therefore the entire supremum is 0. So you actually end up getting mu ax naught, right? And therefore यहाँ पे the similarity value S is nothing but mu A of 32. Now 32 lies between 25 and 35. So this is x minus 25 divided by 10 at x equals to 32. So this is 32 minus 25 divided by 10, and I think this is 0.7. So our similarity value is 0.7, right? And we will use the similarity value to modify our fuzzy set B, which is high, in order to obtain our output fuzzy set B dash. And then having obtained B dash, we will defuzzify it using centroid method as is asked by the question. Okay. So oh, sorry. So our universe starts from 0 and ends at 600. This is our fuzzy set B. S has to be, S is already computed, and that is equals to 0.7, right? And B dash is nothing but minimum of S comma B. That is mu B dash of Y is minimum. And therefore, this is how output fuzzy set B dash looks like. Now we are required to defuzzify it using centroid method. So what is our reason? Our reason is basically this whole thing. Okay. Now I will divide it into two parts. Just a moment, I'll quickly open my notes. Okay. So our region is this. We have to compute the centroid of this particular region. So we first need to compute the area, right? So remember the defuzzified value y equals to is the horizontal coordinate of centroid of region R. So basically green region. And that is nothing but and what is the support here? It's 350 to 600. Okay. So this integral in the denominator is nothing but the area of this region R. So this area can be divided into two parts, right? So R1 and R2. R1 is a triangle and R2 is a rectangle, right? So we will easily infer that 350 to 600 is area of R1 plus area of R2, right? Now, in order to do that, we first need to identify these points, right? This particular point P, because the x coordinate of P would basically help us compute the base of the triangle R1. So how do we compute the point P? It's nothing but the intersection between y equals to 0.7 and y equals to this line. And what is the equation of this line? It's x minus 350 divided by 450 minus 350, which is nothing but 100. So x minus 350 by 100 equals to 0.7 is x equals to 350 plus 0.7 multiplied by 100 is 70, or in other words, 420. So this is 420. Okay. So what will be area of R1? It would be half times base into height. So 420 minus 350 multiplied by 0.7. And what would be area of R2? It would be base into height. So 600 minus 420 times 0.7. And if you evaluate all this, you will end up getting 150.5. Now let us compute this integral in the numerator. This integral can again be uh, uh, divided into two parts. And between 350 and 420, what is your membership function of B dash? It's basically y minus 350 by 100. And what is the membership function of B dash between 420 and 600? It's nothing but 0.7. So when you evaluate this whole thing, what you will end up getting is 1 by 100. So that becomes cube, right? So 420 cube minus 350 cube divided by 3. Then you have 350 divided by 100. So that's 3.5 divided by 450 square, 420 squares, my bad, minus 350 square divided by 2. And then you have the this simple, straightforward 600 square minus 420 square divided by 2. And then you need to do this, divide the whole thing by 150.5. And when you do that, this turns out to be 491.55. So in other words, when your input, that is that input temperature is 32 degrees centigrade, using Mamdani inference scheme, using Mamdani inference scheme along with centroid method for defuzzification, we can infer that the output is, or in other words, the fan speed should be 491.55 RPM, or basically say 492 RPM, right? If we round the number. Okay. So we have talked about Mamdani inference scheme, but if you look a bit carefully, as of now, we have only dealt with one fuzzy if-then rule. And this fuzzy if-then rule was also very simple. Why simple? Because it involved only one input variable x and an input variable y. So in other words, this is an example of a single input, single output fuzzy if-then rule. And in other words, it's also called as a seesaw rule, right? So we have seen Mamdani inference, which is basically this. You given a input A dash, you compute first the similarity value between A dash and A, which is nothing but height of A dash intersection A. And using that similarity value S, you obtain your output fuzzy set B dash in this particular manner. You essentially clip B using S to get B dash. So this Mamdani inference scheme that we have learned so far applies to a single seesaw rule. We have a seesaw rule, single input, single output rule, and we have only one such rule. So we have seen Mamdani inference in the context of a single seesaw rule. But what about multiple seesaw rules? Or what about those rules where you have multiple inputs, right? And that is what we will cover now. We'll cover probably in the next part.